Hi everyone, welcome to the last chapter of the course Organic Compound. In this chapter, you will learn about organic compounds, way to represent organic molecules, how to name organic molecules, isomerism, and functional group. And here is the learning objectives for this chapter. Before we get into the details of organic compounds, let us first define what is organic compounds. Organic compounds are carbon-containing molecules. Majority of the molecule will contain carbon, and there will be some other element that attach to the carbon. So the organic chemistry is the study of the organic molecule or the molecule that contain carbon. The reason why we focus on carbon because carbon is very special and very unique. The reason for that is because first, it can form 4 covalent bonds to itself. And this add diversity to the molecule, right? Because you can change any of these group. And secondly, carbon can form double bond and triple bond as well, even add more diversity to the molecule as well. And lastly, carbon can also bond to itself. We call this catenate, right? That can form either chain, a long chain carbon molecules, or a branch, or even a cyclic ring structures. And with all of these together, that's creating almost nearly million carbon-containing organic molecules. Here are example type of carbon compounds in organism, including carbohydrate, lipids, protein, and nucleic acids. And again, the reason why these molecules are called organic compounds because mainly they contain carbon atoms. Next, we will take a look at the structural representation of the organic compound. The 4 representations that we will take a look at are listed here. Lewis structure, you learned this in Chem 122. We're going to take a look at condensed structure, line structure or line angle structure, and that wedge line structure. Don't worry about this term of hydrocarbon yet. You are going to encounter this again in chapter 19.4. Pretty much the hydrocarbon is an organic compound that contain mainly hydrogen and carbons. Now let's take a look at example 1. In example 1, we are going to use the molecular model of the isopropyl alcohol to help us write out the Lewis structure, condensed structure, line angle structure, and that wedge line structure for this molecule. There is the correction here. The chemical formula that is written here is incorrect. Can you correct that for me, please? The correct chemical formula should contain 3 carbon, represented by the black ball, and 1, 2, 3, 4, 5, 6, 7, 8 hydrogen, represented by the gray balls, and 1 oxygen, represented by the red ball. Therefore, the chemical formula should be C3H8O. Let's start with Lewis structure. We learned in Chem 122 that the Lewis structure of this carbon right here, right, it would connect to 4 bonds. Therefore, the Lewis structure would be carbon connected to hydrogen, 3 of them, and then connected to the next carbon. Okay, so it would be the next carbon. And this carbon here would connect it to oxygen, and that oxygen connected to hydrogen, and this carbon also connected to 1 hydrogen as well. So this carbon right here would have hydrogen and OH, right? And then the next group would be the carbon and then 3 hydrogen connected to it. So there would be carbon and then 3 hydrogen connected to it. So this would be the Lewis structure that we learned from Chem 122. Every atoms will need to have an octet except the hydrogen, right, that have to meet and do it, which means it need to contain 2 electrons. So when we count the number of electron, every bond, they share electron. So each single bond would contain 2 electron sharing. Therefore, if you look at hydrogen here, this hydrogen would contain 2 electrons because 1 from itself, the other from sharing from carbon. This carbon would meet an octet because this carbon would have 1, 2, 3, 4, 5, 6, 7, 8 electrons surrounded. Now with the oxygen here, this is the condensed part of it. If more correctly to write these as the Lewis structure, you can just write out as the single bond as well. If you look at this oxygen right here, right now, oxygen has 1, 2, 3, 4. It's only 4. In order to make it to have an octet, then you need to add 2 more lone pair to the oxygen, right? So now this oxygen would have an octet because contain 1, 2, 3, 4, 5, 6, 7, 8 electron total surrounded. So this would represent the Lewis structure of the molecule. From 122, you learn that the Lewis structure doesn't tell you about the geometry. Note that each of these contain sp3 hybridization, okay, and the sp3 hybridization is what we call tetrahedral, right? So more correctly, the correct structure or the correct geometry of this molecule would be represented as this molecular model because all of these represent tetrahedral, right? So all of these are tetrahedral, including the oxygen as well, right? So this oxygen also adopt sp3 hybridization, which indicate that these are tetrahedral electron domain geometry. Next, let's take a look at condensed structure. Condensed structure is used to simplify the Lewis structure of the organic molecule. If you think about it, the organic molecule are not as simple as this one that we see. Many of them are a huge molecule, is even really complicated. Therefore, to write out every single bond, it's just not very convenient. The condensed structure is when you condense all the hydrogen together with the carbon. For example, this carbon right here contains 3 hydrogen. The condensed part of that would be CH subscript 3 that represent this part that all hydrogen condensed together to carbon. And you are going to connect the bond between 2 carbon again, right? So these 2 carbon has single bond, so you connect that with another carbon. And note that this carbon contain hydrogen and OH group. Therefore, the only thing that you are going to condense is going to be the hydrogen that condensed to the carbon. So you can write as CH, and you will not condense oxygen with the carbon because this is part what we call later functional group. This functional group would be the group that participate in the chemical reaction for the organic compound. So this group is important. So we're gonna write this alone. Okay, so I'm going to write oxygen alone. However, this oxygen right here is connected to hydrogen, so we are again going to condense this hydrogen with the oxygen that is attached to it. Okay, so therefore in this case it would be OH. Okay, and then do the next thing, right? So the next group would be CH subscript 3. So these would represent the condensed structure of this compound. Another way to write the condensed structure is without the single bond between each of these atoms. Okay, so in order to write that, what you can do is you can write as CH3 and then omit the single bond and write next CH. And because the OH is next to the CH, therefore you can do the parenthesis OH that represent that this OH group is still connected to this carbon. Again, it's not going to bond to hydrogen because hydrogen can bond only one bond, right? Can have only one bond. Therefore, it's implied that this hydrogen bond already to the carbon. Therefore, the other group on the right will bond directly to the carbon, and then you can continue to the next one, which is CH3. Okay. Sometimes you can actually see this written out, but have this group to stick out. That is okay as well as for the condensed structure. What do I mean by that, right? So for example, you can write as CH3, CH, CH3, and then have the OH stick out like this too. So therefore, these 3 structure are the correct structure that represent the condensed structure for the organic compound. Either one of these, whatever way that is easiest for you, just stick with that one. But you will need to understand what it means for each of those. Next, we will take a look at the line angle structure. The name already implied that this structure would contain the line and the angle. Therefore, this type structure is going to be the simplified version of the condensed structure. So how can we write this line angle structure is that we are going to omit carbon and hydrogen, okay, and represent only the bond that connects between them. The reason for that is because most of the reaction that involve with the organic compound doesn't involve with the carbon or hydrogen within the organic compound, but is going to involve with the functional group within the organic compound. The functional group are the group of the atom or elements that are not carbon that attach to the carbon containing molecules. Okay, so what do I mean by that? Okay, so let's take a look at line angle structure. The line angle structure represents the bond between the two carbon. For example, in this case, I'm going to focus on this, right? So between these two, there are one single bond that connect between carbon and another carbon. Therefore, we are going to represent the carbon as a dot, okay? And because there are two of them, so I'm going to represent as two dots. We are not going to write out the carbon or hydrogen, but we're going to connect between these two carbon by the single bond. This type is already represented. This carbon right here is connected to 3 hydrogen because it needs to have an octet, right? In order to make an octet, it needs to have those 3 hydrogen. And again, because this part is not participate in the chemical reaction, therefore we can simplify it. So that way it's easier for us to see the structure, okay? So I'm going to go to the next. We already have 1 carbon, 2 carbon, and then I'm going to go to the third one, okay? So in order to write the third one, then you're going to write out another dot here, okay, so to make a zigzag line and then connect the bond there. So these represent the 3 carbon, 1, 2, 3 is represent these 3 carbon. Again, the reason why we do the zigzag because each of these carbon are tetrahedral, right? So the actual molecule is actually zigzag like this, right? So that's why we write like that, okay? Now the group that contain the element other than carbon or hydrogen, we are going to write that as it is. Therefore, in this case, the second or the middle carbon connected to hydroxyl group or OH group, we are going to write that still. Okay, so I'm going to write up, okay, and then write OH group in this case. The hydrogen that attached to the element that is not carbon, you will need to include that hydrogen. You cannot ignore it. Okay, so you will need to still include that. So these would represent the line angle structure of this molecule. Next, we are going to take a look at dash wedge line structure. So the name already implies that you are going to represent this with dash line and wedge line. Okay, so pretty much the dash line and wedge line represent the 3-dimensional orientation of the group. So the line structure will still be the same, right? It's going to be similar to this, except what we're going to do is that I'm going to rewrite the line angle structure that we wrote previously. Okay, so we have this OH. Okay, so pretty much these two are identical, which is identical to this as well. But looking at this carbon right here connected to OH group that's sticking toward you, right? Sticking toward the paper. And this one right here, the hydrogen is sticking away, right, from the screen. So therefore, in this case, the two orientation of these two groups can be represented by the dash line and wedge line. The wedge line would represent, so the dash line would represent things that's sticking out toward us. Therefore, in this case, with the OH group, I'm going to use the wedge line. Okay, so I'm going to use the wedge line to represent the fact that OH group is sticking out toward us. And because hydrogen is sticking away from us, therefore, in this case, we are going to use the dash line for hydrogen that represented is sticking away from us. Okay, so now let me summarize that again. So this wedge line right here representing that's sticking toward us. Okay, so this one right here is away from us. All right, we are going to practice more of this concept for example 2 and 3. Okay, so let's take a look at example 2. Example 2 is giving us the structure of the Lewis structure of this molecule. It asks us to condense this into the condensed structure or the line structure. Okay, so let's go ahead, try to complete these, and when you finish, resume the video again. All right, so let's take a look at example 2. Okay, so example 2, we're going to start with condensed structure first. The condensed structure of this molecule can be written as CH3, right? Dash CH2 and dash again CH2, right? So we are right here now. The next one is still CH2. Okay, the next one connected to C double bond OOH. Okay, so now in order to write out C double bond OOH, you can do C, and then because carbon connected to the double bond oxygen, So you can represent this as the parentheses, right? So parentheses represent that this oxygen directly connected to the carbon, and then another one is OH group that is separate from this oxygen but still connected to carbon, so you still write as OH at the end. Okay, so this parentheses just tell us that it's separate from this OH but is connected directly to this carbon. Okay, so that's one way to write out the condensed structure. Okay, another way to write out the condensed structure is to make your structure without the bonds, right? So it can be written as CH3, CH2, 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 and C parentheses OH. Okay, so that would be another way. The last way that you can represent these can be, you can condense this even further. Okay, the group of CH2 that we see, there are 1, 2, 3. There are 3 of the CH2 group. Therefore, you can use the parentheses to condense that even further to write as CH3 parentheses. We have CH2 group, and because the CH2 group that we have, there are 1, 2, 3, 3 of them. So you can do the subscript 3 outside the CH2 group, right? Because now it's represent that, hey, this CH3 connected to CH2, that are 3 of them. Okay, and then the rest of the molecule would be C double bond OH. Okay, so either one of these would be the correct condensed structure. You can condense like this, or you can condense all the way to the most condensed part, which is this structure right here. Okay, so any of these would be the correct condensed structure. Okay. The next part is the line angle structure. Okay, so the line angle structure, I'm going to start with the carbon. The first carbon and the second carbon contain one single bond. Okay, so I'm going to go ahead, start with that. So we are going to start with dot, right? Represent the first carbon. Second dot would be the second carbon. Okay, so now we are right here, right? So 1, 2, okay, I'm going to connect that. Okay. And then the third one, okay, so I'm going to connect that to the third one. Again, it has to be zigzag line because the geometry of this molecule is actually tetrahedral, because each carbon adopt the sp3 hybridization, which represent the tetrahedral geometry. Okay, so we have 1, 2, 3 carbon. Let's do the fourth one. Okay, so the fourth one would be another zigzag here. So this one represents the first carbon, second carbon, third, and fourth. Okay, so we are 1, 2, 3, 4 now. The fifth one, okay, so let's take a look at the fifth one. Okay, so the fifth one, we go down here. And this last carbon, 1, 2, 3, 4, 5, connected to double oxygen, double bond oxygen, and OH. This group we will not leave out, so we are going to let it let's just be as it is. Okay, so again, because this one is not carbon, okay, and this hydrogen is not connected to carbon, so you will still need to represent this with the element that is not carbon. So therefore, this would represent the line angle structure of this molecule. Okay, so again, the line angle structure would omit the carbon and hydrogen. Therefore, each of these dots would imply that it contains hydrogen. How many? That's when you need to think about the octet rules, right? So this carbon right here, in order to have an octet, it should contain 1 bond, 2, 3, 4. It should contain 3 more hydrogen to have an octet. So this implies that there should be 3 more hydrogen. Same thing for this carbon as well. How do we know whether is how many hydrogen is contained? Well, because this carbon have to have an octet, it already have 2 bonds, so it's missing 2 more. Right, for example. What about this one? How do I know how many hydrogen should it contain here? Well, this carbon right here is already have 1, 2, 3, 4 bonds. It's already have octet. Therefore, this carbon doesn't contain any hydrogen and is matching the structure that we see. Okay, so again, this will represent the condensed release structures, and this would represent the line angle structure. Okay, so let's go ahead, pause the video again, and take a look at example 3, and in this case we are going to look at the condensed structure and draw the line angle structure. Resume the video again when you finish. Alright, let's take a look at example 3. Example 3, we are going to go ahead, count the number of carbon here. Okay, so that way it's easier for us to know how many dots we need to connect. Okay, so I'm going to go ahead, count this 1, 2, 3, 4. Okay, so and carbon number 4 contain the oxygen in parentheses and NH2. So I'm going to go ahead, write out the 4 carbon first. So 1, 2, 3, 4, and I'm going to connect them with one single bond. Okay, so let's do that. Okay, so actually my bond is not very pretty, so I'm going to redraw that. Okay, so let's do 4. All right. So the next thing we are going to take a look at is we are going to take a look at carbon number 4. Carbon number 4, the last carbon right here, okay, connected to parentheses oxygen, well, which means that you are going to separate oxygen alone, right, away from this NH2, right? That's what parentheses mean, is stay away from this group, but it's connected to this carbon. And this NH2 group will directly connected to this carbon right here. So I'm going to go ahead, write out NH2 here. Okay. Now, the next thing that we will need to look at is we will need to make sure that all the carbon contain octet, right? So let's take a look at this carbon. This carbon here, if you draw only one bond to the oxygen, this carbon would lack of octet, okay? And it doesn't have any hydrogen that attached to it. Therefore, I can't just leave as a single bond. Therefore, in this case, to make both carbon and oxygen to have an octet, all I need to do is draw double bond between carbon and hydrogen and oxygen, okay? And for this carbon right here is already have an octet. That's good. Okay, so this hydrogen will leave as it is because that's the group that is given to us. This hydrogen right here, to have it to make an octet, you just need to add just one lone pair here, right? So oxygen would need 2 lone pair here. Now let's take a look at the first carbon real quick. The first carbon contains 3 hydrogens, so it would be 1, 2, 3. This carbon would contain octet. That's good. This carbon right here contains just 1 hydrogen, so I'm just going to go ahead, write that out real quick, and we can erase this later. And the third one contains also 1 hydrogen as well. If you think about these 2 carbon is lacking of octet, right? Because each of these contain single bond to carbon, but only 1 bond to hydrogen. Therefore, these 2 carbon is lacking of octet because contain only 1, 2, 3, 4, 5, 6 hydrogen. Therefore, this is when you will need to connected them with the double bond. Okay, so same thing that we did earlier. So we're gonna connect this as double bond. And after you're done, just make sure that you eliminate the hydrogen, right? So that way we have the actual line angle structure. So this line angle structure would represent this molecule right here, right? Because contain carbon with 3 hydrogen, carbon with 1 hydrogen, carbon with 1 hydrogen, carbon with C double bond O and NH2. Okay, so this would be the Lewis structure of this compound. Now let's take a look at the next thing. I'm gonna do the same thing. Okay, so go ahead, number each of those carbons. So it would be 1, 2, 3, 4, 5. Okay, so we have 5 carbon. So I'm gonna go ahead, do the same thing. Oh, wait a second. Before we do that though, let's take a look at this. We have the parentheses CH3. Okay, so again, anything that is in parentheses, it just means that it's going to be separate from the atom from the right? So that means this one is not going to connect to that, but it's going to connect directly to the atom, the carbon atom on the left. Therefore, I'm not going to actually write this as number 3. I'm going to renumber it again because this group right here in the parentheses will connect directly to that group. Therefore, our main group would contain 1, 2 carbon, and this would be the 3rd one, and this would be the 4th one. Therefore, in this case, when I draw the line angle structure, I will start with the 4 carbon. Okay, so 1, 2, 3, 4. Okay, and we know that the first one, right, contain 3 hydrogen, so that's already have 3 hydrogen right there, 1, 2, 3 that we ignore. The second one has 1. Okay, and another one is CH3. So this is when you will write out CH3. Okay, so which is this group right here. The reason why I don't write out CH3 because again the carbon is represented by the dot right there, right? It's already implied that this dot right here contain carbon that connected to 3 hydrogen. Okay, so this carbon is represented by this carbon right here. Carbon number 2 is this carbon right here. It contains CH3 and it's also contain hydrogen as well from this. So that means this carbon already have an octet. Okay, The next carbon is CH2. Okay, so CH2, so C and then H, 2 hydrogen, that would also meet an octet as well. The last one is carbon that connected to hydrogen and connected to oxygen. Okay, so that means in this case, I'm going to connect this to oxygen. Okay, so this carbon right here at the end is a carbon that connected to hydrogen and one oxygen. Therefore, if you look at it, this carbon doesn't have an octet yet. Therefore, you will need to add the double bond between the carbon and oxygen. If you are not sure about the octet rule for each atoms in the molecule, you can go ahead write out each of these atom, right? So you can write out CH3, right? So this would be hydrogen, and then you can write out CH, right? And then this CH3, this CH2. Okay, so you will see that all of these would already have octet. But before you answer this is not the line angle structure, so make sure that if I ask for the line angle structure, you will need to eliminate all of these hydrogen and carbon. So therefore, the correct structure would be when you erase off these carbon and hydrogen. Okay, so therefore, in this case, the correct structure would be as I'm going to write here, right? So it's going to be as we determined earlier. So it would be 1, 2, 3, 4 with the CH3 right here. So this would be the correct line angle structure.